All right, let's take a look at our warm up here. Basically, just got some basic probability questions. So, probability is 0.13 that a person chosen did not complete high school, 0.29 that they have a high school diploma but no further education, and zero point 0.3 that they have at least a bachelor's degree. So A says, what must the probability be that a randomly chosen young adult has some education beyond high school, but does not have a bachelor's degree? All right, so this is basically just, which piece of the pie is missing. Probabilities always have to add up to 1 when you're looking at the entire sample space because it represents all options, so 100%. So if we're taking away the 13% that didn't complete high school, and we're taking away the 29% that have high school but nothing more. And then we take away the 30% that have a bachelor's degree or more. All that leaves, because we've just run through all the possibilities, are the people that have more than high school but have not yet earned a bachelor's degree. So maybe they have a trade school, maybe they have an associate's degree, maybe they're working towards their bachelor and they just haven't finished it. Whatever it is, doesn't really matter. But it's this idea that 1 represents everything, 100% of the possibilities. So if we take away those, whatever's left over has to be what fits in that 4th category there. All right. Now, the only reason this works is because we've sort of accounted for all the possibilities. Like if this had just said, chosen young adult has an associate's degree, we wouldn't necessarily have enough information to answer that question because, all right, maybe they are only a year into their associate's degree, or maybe they, I don't know. I don't even know where I'm going with this. Other than the only reason we're able to do this is because we're accounting for all the possibilities here. All right. And these 3 categories, along with this 4th category here, gives us the complete range of options or the entire sample space. What is the probability that a randomly chosen adult has at least a high school education? All right, so that then becomes taking a look at our different situations here. We can say, all right, that would include the 0.29 that has a high school diploma. It would include the 0.28 that has more than high school but not a bachelor's. And it would include the 0.30 that has a bachelor's or more. All right, so that adds up to, assuming my math is right, 87%. Now, the other way of getting that, and again, this is just sometimes taking notice of compliments because it'll make your life easier, is just saying, oh, well, that's just 1 minus the people that didn't complete high school. Either way, you're getting the same 87% that we're looking for on that one. Okay. A company that offers to prepare students for the GMAT has the following information about its customers. 20% are undergraduate students in business, 15% are undergraduate students in other fields of study, 60% are college graduates who are currently employed, and 5% are college graduates who are not employed. Now, a quick look at those numbers. 20% plus 15% plus 60% plus 5% shows us that adds up to 100%. So we can be confident that we've sort of accounted for all possibilities at this point. So it says, what is the probability that the customer is currently an undergraduate? That would just be the 20% plus the 15% or the 35%. And then what's the probability that the customer is not an undergraduate, which means they're not still in, their first 4 years of college? You either say, okay, well, that's 60% plus 5%, or you just say that's 100% minus the 35% we just calculated. Either way you slice it, you're going to end up with that same value of 65%. All right. So again, nothing tricky going on here. Just this very basic concept of all the possibilities represent 100%. And then we're just using that to find any missing pieces, or here we're not even doing that. We're just verifying that they add up to 100% and then combining whatever categories we need to combine. Number 3, not all dice are weighted evenly. The following figure displays several possible probability models for rolling a die. We can learn which model is accurate for a particular die only by rolling it several times or many times. However, some of the models are not legitimate. That is, they do not obey the rules. Which ones are legitimate, which ones are not? In the case of the legitimate models, explain what is wrong. All right, so there's actually only one legitimate model here. All right, this is the only legitimate one. All right, model 1 is illegitimate because the probabilities sum to less than 1. Less than 1. All right, and with a probability model, all the probabilities should always sum to 1. All right, I'm going to shorten this up so that each one is a little shorter. Model 3 is bad because the probabilities sum to more than 1. All right, so that means they're summing to more than 100%, which doesn't really make sense. Model 4 isn't even giving us probabilities. And then the only one that's okay is model 2 is good because they sum to 1. All right, so again, there's nothing saying that they all have to be 1/6. All right, it says not all dice are weighted evenly. So maybe there's some way that this die will never show up as a 4, but it's more likely to show up as a 1. Whatever the case may be, this one only adds up to 6/7. This is the only one that adds up to 1. So how do I want to write that? We'll write it as, I'm just going to write it as a 1. This one right here adds up to 1, 2, 3, 4, 5, 7/6. This one right here is ridiculous. It adds up to 4, 8, and doesn't even make any sense. So the only one that's a valid model is this one that's adding up to 1 here. Okay. Human blood can be typed as one of O, A, B, or AB, but the distribution of types varies a bit with race. Here's the distribution of blood type by randomly chosen African American. All right, so we've got 0.49, 0.27, 0.2, and then assuming that this encompasses all the possibilities, we know these have to sum to 1. So again, 1 minus 0.49 minus 0.27 minus 0.2. That's 4.7 plus another 4.8, 4.9 is 9.6, which means we're left with 0.04 here. All right, so this is going to be 0.04. So what is the probability that a person chosen does not have type A blood? Again, same idea as we were doing on the front here. You can either say 0.49 plus 0.20 plus 0.04, or you can just say 1 minus 0.27. Either one of those is going to give you the same answer, which is 0.73. And I know these seem really basic right now, but this idea of using the complement to your advantage is going to become really important later on when the problems get a little more involved and they're less straightforward than what we're seeing here. So we're just getting used to the concept here so that it's not foreign to us when we have to apply it to something a little more involved. All right, if someone has type B blood, they can safely receive transfusions from people with blood types O and B. What is the probability that a randomly chosen African American can donate blood to someone with blood type B? All right, so that's basically just saying O and B added together. So it's just doing the 0.49 plus the 0.20, which gives us 0.69. All right. So again, nothing really tricky going on here. Pretty straightforward. But again, if you have any questions, let me know. This is the only one that's maybe a little less than intuitive, but it's basically just this idea that it always has to sum to 1. All right. Have a great day, and I will see you when I see you. Bye.